In the boundless realms of space, life takes on an entirely new dimension, challenging both human survival instincts and scientific ingenuity. The introduction to our script unveils the concept of living in the vast expanse beyond Earth, an awe-inspiring yet perilous venture. Living in space can be defined as humans' ability to sustain life beyond the Earth's atmosphere, which involves unique challenges like microgravity, radiation exposure, and the need to provide constant life support, including air, water, and food. The significance of understanding life in space is profound. As humanity sets its sights on deeper exploration, ventures like missions to Mars and beyond, mastering the art of survival off Earth is critical. It not only ensures the safety and success of astronauts, but also paves the way for long-term space habitation, propelling us closer to becoming a multi-planetary species. Real-world examples abound. Take the International Space Station, which serves as both a home and laboratory for astronauts. On the ISS, astronauts practice farming with hydroponics, a soil-less, plant-growing method, hinting at sustainable food sources for long-duration missions. Another example is the meticulous recycling system on the ISS, where 93% of water, including sweat and exhaled breath, is reclaimed and purified. A vital process ensuring astronauts have a continuous supply of potable water. Experts and space enthusiasts champion the idea that understanding and advancing how we live in space elevates our scientific knowledge and inspires global cooperation. Space agencies like NASA and ESA continually emphasize the collaboration necessary for facing the unknowns of space habitation. However, surviving in space is fraught with challenges and controversies. The financial burden of sustaining life in orbit is enormous, with questions about whether these funds might be better spent on pressing Earthbound issues. Additionally, space environments pose health risks, such as muscle atrophy and radiation-induced illnesses, sparking debates on the ethical implications of exposing humans to such dangers. The concept of living in space intricately connects to other facets of human space exploration, influencing technological advancements and inspiring policies and regulations for future missions. As we delve deeper, we discover that every aspect of surviving off Earth, from engineering breakthroughs to international agreements, contributes to the overarching goal of expanding our presence throughout the cosmos. With this foundation, our journey into the science of living in space begins, promising insights that will shape our extraterrestrial future. Human physiology adapting to microgravity is one of the most crucial aspects of how astronauts survive in space. When we talk about microgravity, we refer to an environment where the gravitational forces are much weaker than on Earth, resulting in a sensation of weightlessness. This condition fundamentally alters the human body, necessitating a deep understanding of how to adapt to and mitigate these changes to ensure astronauts' health and mission success. The significance of grasping human physiology in microgravity is paramount. Space missions, whether on the International Space Station or potential journeys to Mars, place astronauts in environments where Earth's gravitational pull is absent. Prolonged exposure to microgravity can lead to muscle atrophy, bone density loss, fluid redistribution, and alterations in the cardiovascular system. Understanding these changes is vital not only for the well-being of astronauts during their missions, but also for ensuring they can readjust to Earth's gravity upon return. Real-world applications highlight these challenges and adaptations. Space agencies implement rigorous exercise regimens, utilizing treadmills and resistance devices on the ISS to counteract muscle and bone loss. Astronauts like Scott Kelly, who spent a year in space, provide invaluable data on long-duration microgravity's effects. His experience aids in developing better countermeasures for future missions. Experts in astronautical physiology emphasize the importance of continuous research and innovation. Scientists like Dr. Jennifer Fogarty from NASA's Human Research Program advocate for understanding individual variability in response to microgravity, ensuring tailored approaches for astronaut health. However, challenges persist. One controversy revolves around the unknown long-term effects of microgravity, especially as missions extend beyond current parameters. Although exercise mitigates some negative effects, it's not a complete solution, and the complexity of human adaptation remains an area of active research. Alternative viewpoints suggest artificial gravity as a potential solution, yet its feasibility remains debated due to technological and financial constraints. The study of human physiology under microgravity doesn't exist in isolation. It directly influences spacecraft design, mission planning, and the development of life support systems. These adaptations are interconnected components, collectively ensuring astronauts not only survive, but thrive in the harsh environment of space. By understanding and addressing these physiological challenges, we pave the way for the future of space exploration, aiming for longer, farther-reaching missions that push the boundaries of human possibility. Space nutrition is the intricate science of providing astronauts with the necessary sustenance to maintain their health, performance, and survival in the unique environment of space. This concept involves understanding how the absence of gravity, limited access to fresh supplies, and the isolation of space can impact the dietary needs and consumption patterns of astronauts. The focus on space nutrition is vitally significant as it directly influences an astronaut's ability to carry out missions effectively, ensuring they have the energy and resources necessary to adapt to and overcome the challenges of living off Earth. One exemplary application of space nutrition is the development of space-friendly foods that are compact, nutritious, and easy to prepare in zero-gravity environments. For instance, the creation of space food pouches, which contain pureed or processed foods sealed in flexible packaging, allows astronauts to conveniently consume meals without dealing with potentially dangerous crumbs or spillage. Another example is the cultivation of crops aboard the International Space Station, such as the Veggie Project, which successfully grew red romaine lettuce. This experiment is a real-world application that demonstrates the potential for self-sustaining food sources during prolonged space missions. Several experts and organizations emphasize the critical importance of advancing space nutrition as a cornerstone of successful space exploration. The continuous research and innovation in this field are viewed as essential not only for maintaining astronaut health, but also for paving the way toward feasible long-term habitation on other celestial bodies. However, the journey to perfecting space nutrition is not without challenges. Microgravity poses a significant obstacle as it alters taste perception and affects how liquids and solids move, complicating meal preparation and consumption. Additionally, the limited shelf life of many foods, the need for packaging that withstands radiation and extreme temperatures, and the psychological impacts of a repetitive diet all require ongoing research and solution development. Alternative viewpoints stress the importance of balancing nutritional content with psychological comfort and cultural food preferences, which also affects space mission success. Space nutrition is intricately connected to other aspects of living in space, such as physical health, psychological well-being, and mission logistics. Proper nutrition supports muscle and bone health, which are both adversely affected by prolonged exposure to microgravity. Furthermore, ensuring astronauts have satisfying, comforting meals can mitigate feelings of isolation and stress, ultimately leading to a more successful mission. Through these connections, space nutrition is not merely a consideration, but a critical component of successfully surviving and thriving off Earth. In the vast expanse of space, where resources are limited and resupply missions are costly and infrequent, astronauts rely on water and air recycling systems as their lifeline. These life-sustaining systems are engineered to mimic Earth's natural processes, ensuring that astronauts have the essentials they need to live and work. Water and air recycling involves the purification and reutilization of onboard resources. On the International Space Station, this means turning sweat, urine, and exhaled breath into drinkable water and breathable air. These systems are crucial for long-duration missions, preserving vital resources and reducing dependency on Earth resupply. One significant system is the environmental control and life support system used on the International Space Station. This system recycles up to 93% of the water used on board, turning what might have been waste back into usable water. It also includes a CO2 removal unit, crucial for maintaining the right balance of breathable air. Another example is the oxygen generation system, which splits water into hydrogen and oxygen via electrolysis, thus providing a continuous supply of breathable oxygen. Experts in space exploration emphasize the necessity of these systems for future missions, particularly as we set our sights on Mars and beyond. Dr. Jennifer Fogarty, former chief scientist at NASA's Human Research Program, notes that sustainable life support systems are paramount for the feasibility of long-duration space travel. Challenges exist, however. The technology is complex and must work flawlessly in the harsh environment of space. Any failure could compromise astronaut safety, making redundancy and reliable maintenance crucial. Critics also argue the cost and complexity might be prohibitive, especially for smaller missions or organizations new to space exploration. Yet, these systems interlink with many other aspects of life in space. They influence everything from the design of spacecraft habitats to the psychological well-being of crew members who benefit from dependable life support. As we consider extended missions, these systems will play a key role in determining how self-sufficient spacecraft can become, impacting mission planning and the design of future astro-settlements. Water and air recycling are not just about survival. They are fundamental to advancing humanity's reach into the stars, ensuring sustainable and safe human presence beyond Earth.